In today's lesson, we're going to start taking a look at E1 oscillations. And an oscillation is a periodic varying of a position of a system about a point. So the system could be anything that you could think about that is repeating its position about some central point in a rhythmic or consistent fashion. A couple of examples of oscillations that are relevant. We'll be looking a lot at masses that are bouncing on springs. This has a lot of application for different types of engineering and technological aspects of machinery that we see in our environment. Another very common one that we'll look at in depth is a pendulum. And when we talk about oscillations, ultimately what we're really going to want to get at is talking about the energy and the momentum of systems as they oscillate. When we talk about oscillations, the one thing that we want to keep in mind is restoring force. In order for an object to be moving and oscillating about some point, something must be pushing it back and forth between its positions. So if it is oscillating about some point, imagine, say, like a piece of wood that is bobbing up and down in the water. There's always has to be something that's pushing it up and down in the water for it to be oscillating. In the example of the object that's bobbing in the water, it's gravity that's pushing it down and the buoyant force that's pushing it up. So as it pushes up and down on the surface, we have forces that are acting on it that are trying to restore it to its position. Restoring forces always act towards the equilibrium position. Whenever you have an oscillating system, it's always going to incur or have to have restoring forces. The reason why objects oscillate is because the energy that's gained and the momentum that's gained by the restoring forces that pushes it back to its centralized position gives it a certain amount of momentum. But when it reaches its position that the restoring force is pushing it towards, at that juncture, it has momentum. So it passes through that point in the system, goes right by that centralized position, carries it past that position, or another restoring force in the opposite direction develops, pushing it back towards that original position, and it can't get the energy and the momentum out of the system, so it keeps on repeating itself. When we talk about oscillations, there's a couple of terms we have to be very keen about. The first one is period. Period is the time it takes to complete one oscillation. We measure period in seconds. Another one is frequency. Frequency and period are inverses of each other, so they're another way to look at really the same information. Frequency is defined as the number of oscillations that occur in a unit of time, and frequency is measured in hertz. And then a third one, which is somewhat familiar, is angular speed. Angular speed is the rate at which oscillations occur per unit time. Now, this is the same angular speed we looked at when we talked about rotational motion. Objects that are rotating are also oscillating after a fashion. So when we talk about angular speed, we talk about it in terms of radians per second, and we want to measure that the same way that we do when we talk about rotating objects. So we talk about how many radians occur in 1 second. Recall that when we talk about an object that's rotating, if it went through 2 pi radians, you would end up having 1 full oscillation. So anything that's rotating, 2 pi radians, that's 1 oscillation. So we can look at angular speed as oscillations per second. We have equations that relate the relationships between period, frequency, and angular speed. The first one is one that you're familiar with. Is period is equal to 1 over frequency. They're inverses of each other. Of course, this means that frequency is equal to 1 over period. But what we really want to get to is a discussion about angular speed. So we want to relate angular speed to both period and frequency. We can say that angular speed is equal to 2 pi divided by period, or we could say it's 2 pi times frequency. The 2 pi is relevant because within 1 full oscillation, there is 2 pi radians. And this takes its idea from the unit circle. So if you go 2 pi around a circle, that means you've completed 1 oscillation, just like we looked at 2 pi being 1 full circle in rotational motion. 2 pi represents 1 full oscillation within angular speed. I want to be clear that when you talk about angular speed for something like a mass on a spring or a pendulum, we represent 2 pi as the rate, or as 1 full oscillation, as opposed to 1 full circle. Let's go ahead and try an example of this. In this example, an observer counts 20 complete water waves passing by the end of the dock every 10 seconds, and we want to figure out what the angular speed of the waves is. To do this, to determine angular speed, we need to at least start with initially either frequency or period. In this example, we're going to look at period. And we'll say that period is the time divided by oscillations. So this is how long it takes one oscillation to occur. If there's 10 seconds, we observe 20 oscillations, and that means it takes half a second for each oscillation, right? 20 oscillations, 10 seconds, a half second for each oscillation. That is our period. Once we have our period, we can determine what our angular speed is by taking the angular speed is equal to 2 pi divided by period. Here we have 2 pi divided by 0.5 seconds, and we find an angular speed of 12.6 radians per second. So that's the angular speed of this example. What I'd like you to do is try an example of this, and then we will try some further oscillation problems.